Question is related to electromagnetic effects. Draw a label diagram for the structure of a basic step down transformer. So we need a step down transformer. So this will be the iron core, and there will be turns for the primary. Which one should have more turns, primary or secondary? Primary, because it's a step down, so secondary should have less turns. It should be labeled. So this is the iron core. Label this as a primary coil. Label this as second. I'm writing in short, but write primary, and here it should be a power supply. Explain the operation of a basic transformer. How transformer work? What is the working principle of transformer? 3 points are important. AC input produce a variable magnetic field. AC input in the primary produce variable magnetic field, and which magnetize the iron core. So this iron core will be magnetized, and change in the magnetic field of iron core, what will happen? It will induce EMF in the secondary, and which can be step up or step down by using a suitable turn ratios. The voltage of a main supply is 230. The output voltage is 6. You need a turn ratio only. So we have the formula. Solve this. First, write the formula. Okay. So Vs over Vp equals Ns over Np. We need this. So voltage of a secondary is 6. Voltage of a primary is 230. So when we divide, it was 1 ratio. Sorry. Okay. So 3 ratio 115 will be there. So this will be the turn ratio. It can be any multiple. Even you write 6 over 30, that is also acceptable, because they just mention a turn ratio. When you mention 0.026, usually when they write the turn ratio, yeah, it's written 0.026, but you can also write in fractions as well. The electromagnetic force, two straight wires which are vertically carrying the current. Wire X and Y passes through a holes. Figure 8.1 shows a card which is viewed from above. So we are looking at these wires from the top. So why these wires will experience a force? First, X will produce a magnetic field. So Y is in a magnetic field of X, and X is in a magnetic field of Y. So two wires are in the magnetic field of each other. That's why they will experience a force. There's a current in each wire downward or into. The magnetic field at Y due to current in X produces a force on Y. Means there's a magnetic field at Y, like this Y is having a magnetic field because of X. Like X magnetic field is passing through Y. And because of this magnetic field and the current, it experiences a force. Place a tick in each column to indicate the direction of magnetic field and the direction of force. First, to find the direction of magnetic field. So if you want to work out the direction of a magnetic field, which rule we'll use? We'll use a right-hand grip rule. So X magnetic field is passing through Y. So we have to use a right-hand grip rule. Your thumb represent the direct right-hand grip rule. Right-hand grip rule, the thumb represent the direction of the current and fingers will turn around. This is called a right-hand grip rule, which is used to find direction of magnetic field. So the magnetic field of X will be circular. And what about its direction? It will be in this way. Because when you apply the rule, your thumb is pointing into and fingers turn around. So the magnetic field of X is clockwise. Now, what is the direction of a magnetic field of X on Y? Which direction it is pointing? What is the direct? What is this direction? Direction of a magnetic field of X on Y? Downward. So the magnetic field is acting downward. So you will mention like because the question was place a tick, place a tick, the magnetic field at y. So magnetic field at y is due to x. And what is the direction? So it is towards the bottom of the page. The next part is the force. Which direction it will experience a force? So for a force, you have to use a left hand rule. Your index finger will point, like now you have to apply a left hand rule on y. Your index finger point in the direction of magnetic field. What is the direction of magnetic field? Downward. So your index finger should point downward. Use the left hand rule. Your index finger should point downward. Your second finger represents the direction of the current. The current is into. Use the left. Index finger pointing downward. Second represent the direction of the current, which is into. Where your thumb is pointing? To x. So the direction of the force is towards x. And remember one thing, even without applying the rule, you can also work out. So the direction of the force is towards x, or it is towards the left hand side. So if you want to complete this, what is the direction of a magnetic field? It was towards the bottom. And what is the direction of the force? It was towards left. There is also a simple way to remember whenever two wires are carrying a current in the same direction. Whenever two wires are carrying current in the same direction, like example cross. So what is the direction of the force? The direction of the force is towards each other. If two wires are carrying current in the same direction, like dots, means out. What is the direction of the force? The direction of the force is towards. But if one is carrying in, another one is carrying out, so what is the direction of the force? The direction of the force will be opposite. So this, without applying a rule, I can also work. If they are carrying the current in the same direction, so definitely how the force will be, it will be in this way. Okay, you can apply a rule and work out, or you can also use your understanding that if one wire is carrying in, another one is out, what is the direction of the force? It will be away from each other. Is it clear, this one? Is it clear? Any doubt? Abdul Aziz, Ghulam, Hamad, Imad, Ammar, Muhammad Ali? State and explain whether there is also a force on y, on x, wire x. So you will say yes, because the reason is that x, the wire x cuts the magnetic field of y. Figure 8.2 shows a DC supply. The transformer work with AC, or it can also work with DC on only two conditions. When you open the switch or you close the switch, then only the transformer work with DC. Otherwise, it will not. The moment we open that short interval, it will work, or we close the switch, then also it will work. But with AC supply, it will. How we identify which flux is, it's always the opposite. Like whenever two wires are there, say you have A and B are the two wires. So wire A is in a flux magnetic field of B, and wire B is a magnetic field of A. So they always cut the opposite magnetic field. So the DC supply, the figure shows a DC supply connected to an input transformer. When a switch is first closed, the needle of a galvanometer deflect briefly and then return to zero. Why deflect? So when we close the switch, because the moment we close the switch, even the DC supply a constant current, but it won't be constant from the beginning. How the current, for example, this DC supply provide a constant current of 2 amperes. So say provide a constant current of 2. The moment we close the switch, so it will reach 2 and then it will be constant. So this part, the current is changing. So the moment we close the switch, there is a change in a magnetic field for a very short time, and that change in a magnetic field induces EMF in the secondary. But then why it becomes zero? Because the current is constant. If the current is constant, there is no change in magnetic field. That's why there is no induced EMF. This question is related to electrical circuit. Figure 9.1 shows a 12-volt battery connected to a circuit containing resistor A, B, C, D. Each resistor has a resistance of 6 ohm. Calculate the combined resistance of AB. If 6 ohm, each is 6 ohm. What is the combine of AB? Just add them because they're in series. So when they're in series, we simply add. So it will be 12. Then what is the combine? The next is combine of ABC. So this is 12 and this one is 6. Like these two collectively 12 and the other one is 6. What is the combine? It will be product divided by sum. Yeah, that's right. 4. It will be 12 into 6 divided by 12 plus 6. So that is 72 divided by 18. That is equals to 4 ohm. And then combine of, so this total is 4 and this is 6. What is the combined resistance of whole circuit? 10. Because this 4 plus 6 will make the sum 10. The next is calculate the current in the battery. So how to work out the current in the battery? We know the total resistance of this whole part of a circuit, which is 10 ohm. And what is the total current? The same current will pass through D. Because the total current enter the circuit, it will divide in the branches and then it recombines, so the same current will flow out. So if we need the current, V equals IR. So current is voltage divided by resistance, so 12 divided by 10, which is 1.2 ampere. So this 1.2 will divide between the branches, but what will the current here? 1.2. And then say 1.2 will return. The energy transfer from the battery in 50 seconds. So if we need the energy, we need VIT, because the energy transfer is voltage into current into time. V is the voltage, which is the voltage of the supply. What was the voltage? 12. So it was 12 multiplied by 1.2 multiplied by 50. So you got 720 joules. This question is related to electromagnetic effect. A bar magnet is made up of a metal, suggests from which bar magnet is made, because it's a hard magnetic material, so it is made up of steel. If it was an electromagnet or temporary magnet, then we'll mention iron. Figure 8.1 shows a bar magnet inserted into a coil. The north pole and the south poles are marked. The coil is connected to galvanometer. Why the galvanometer deflect as a bar magnet is being inserted in the coil? So when we move the bar magnet towards the coil, why there's a deflection in the galvanometer? So you can mention the coil cuts the magnetic field, or there's a change in the magnetic field or magnetic flux linkage, and the change in the magnetic flux linkage induce EMF. And because of this induced EMF, because the circuit is closed, then it will produce a current. So list these points. When the bar magnet is moved, there's a change in magnetic flux linkage. Change in magnetic flux linkage induce EMF. Induce EMF produce a current because it's a closed circuit. If it was not a closed circuit, what if we were having like this, that there was a switch here? Then there will be induced EMF, but there will be no current. Why? Because the circuit is not complete. So 3 points you have to list here. What determine the direction of a reading on galvanometer? So what determine the direction of reading on the galvanometer? Like how much it depends on the speed at which we move the magnet. It depends on the number of the turns. It depends on the strength of the magnet. These And the direction of a deflection depends on which pole we are moving in which direction. So the EMF induced depends on three factors: the number of coils which we use, the magnet, the strength of a magnet, and it also depends on the speed. But the direction of the deflection, which direction the needle will deflect, that depends on two factors. It depends on which pole we are moving, and it also depends on which direction we are moving the magnet, means move towards or away. Describe a method of demagnetization of a bar magnet is not part anymore. You don't have to learn methods of magnetization and demagnetization. So this was page 25.